For more information on tutoring or how to support Moof University and the production of more videos, please visit moofuniversity.com. Thank you and enjoy. So in this video we'll discuss atomic spectra and specifically the hydrogen spectrum and the Rydberg equation. So here we have a sun, and the sun gives off light. We got sunlight. If we take that sunlight and pass it through a thin slit like we got here, specifically this portion, this little hole, we can take the sunlight, pass it through a slit, and then following that we'll pass it through a prism, a glass prism that will refract or bend the light, and what we'll see is a spectrum that looks like the rainbow, right? Maybe some of you have actually done this before. Shined light through a prism and saw that it would project a sort of rainbow like this. Now, this is a spectrum of colors, of course, going from violet to red, and the colors are changing continuously. So this is a continuous spectrum. One color kind of blends into the next one, and we progress from violet to indigo to blue, green, yellow, orange, and red. Okay. Now, this isn't the best depiction out there for a spectrum. I'd encourage you to look up a better image than this, but you can see how the colors can continually change from one to the next. Okay. Now, atoms, they can be excited by heat, thermally, or by electrically, to give off light as well, and that light can be passed through a slit and refracted as well. However, the result is that it's not refracted in quite the same way. So here we have a tube of hydrogen gas. This is hydrogen gas here. And the light, it's excited, okay? And when it is excited, it gives off light that we're passing through a slit, just like we did before, followed by a prism, and then that light is refracted. And we get a spectrum here as well, but not quite the same. So here, instead of seeing continuous color changes, we see thin lines, each of different colors, with darkness in between them. This is a line spectrum. Okay, so we see thin lines that are sort of shaped like the slit is, and these lines are of different colors that have corresponding wavelengths, and in between them is just darkness. Okay, now this is specifically hydrogen's line spectrum. So here we have hydrogen's line spectrum. We've got the wavelength in nanometers going from 400 to 750 here. So we've got violet it's at about 410.1 nanometers. The blue line is at 434.1. The green line is at 486.1. And the orange line over here is at 656.3. Okay. Now notice that I only put the visible portion of the spectrum here. There are other parts of it that are just not shown for simplicity's sake. So the question is, what does this mean about this hydrogen line spectrum? What's the point of this? Well, what this means is that the hydrogen atom emits only certain values or certain quanta of energy, right, that correspond to these different wavelengths and the colors. Okay. So when we're talking about atomic line spectra, an equation that's often associated with it is the Rydberg equation. Okay. The Rydberg equation. And the Rydberg equation is this: 1 over lambda equals r parentheses 1 over m squared minus 1 over n squared close parentheses. So what is this thing? Well, lambda refers to wavelength in meters, which we've seen before. And r is new. R is a constant, specifically the Rydberg constant, and it's equal to 1.096776 times 10 to the 7th, 1 over meters, right? So the units here are basically the reciprocal of the units here. M and n are integers that are unitless, such that n is greater than m. Okay? They do not have a unit. What's the purpose of this Rydberg equation? It's used to predict the wavelength of any line or lines in a series. Okay. Now, if m equals 1, that corresponds to the ultraviolet series, or the UV series. If m equals 2, that corresponds to the visible series. If m equals 3, we're talking about the infrared or IR series. Okay. So this part might not make a lot of sense quite yet. It'll make hopefully a little bit more sense in the next video on the Bohr model. Okay. Now let's do some practice problems that relate to the Rydberg equation. So here we got a question with two parts, A and B. So A says, given that m equals 1, what is the longest possible wavelength in the spectrum? So they tell us that m equals 1, and they want us to find the wavelength. So what I'm going to do is I'm going to basically solve the Rydberg equation for wavelength and go from there. So if the Rydberg equation is this, I'm going to solve for wavelength by first writing the equation as it's given. So 1 over wavelength equals r times 1 over m squared minus 1 over n squared. So basically, if I cross multiply here, if I just put this, can I erase this a little bit? If I just put this over 1 and I cross multiply, I get if I just cross multiply here, I get 1 equals lambda r times 1 over m squared minus 1 over n squared. And then I could just divide both sides by this whole thing except the lambda. So r 1 over m squared minus 1 over n squared. Do that to both sides. 1 over m squared minus 1 over n squared. And then here this cancels. Okay. And then I'm just left with lambda equals 1 over, that whole thing would be r 1 over m squared minus 1 over n squared. Okay. So I've solved it for wavelength. And I've done this because they're asking me what is the longest possible wavelength. So they want me to find the wavelength. Now, they tell me that m equals 1. Okay, so m equals 1. And I also know that the r is just a constant, right? So I'm going to plug that in. So I'll have 1 over, I'm going to round to a few sig figs here for the constant. I'll just have 1.097 times 10 to the 7th, 1 over meters. And 1 over 1 squared is just 1. But I have minus 1 over n squared. Okay. So what's going on here? Now I don't know what n is. They didn't tell me what n is. So, but they did tell me they asked me what is the longest possible wavelength in the spectrum. And I think that's best shown purely by just giving you the example here and showing you, just telling you first of all, that n will be the wavelength will be longest when n is as small as possible. Okay. But remember that n has to be greater than m. So the smallest value that I can put here is 2. Okay, so that's what I'll do. Plug in a 2 here. So I'll put, let's just make this quicker and easier because I have technology here. I'll replace that n with a 2. So I have 1 minus 1 over 2 squared, which is 4. So I'll have 1 over this constant, 1.097 times 10 to the 7th, 1 over meters. And then this is going to basically be 1 minus 1/4, right? Which is just 3/4. So I'm going to write that here, 3/4. Okay. And if I plug this into my calculator, I will get 1.215 times 10 to the negative 7 meters, which also equals 121.5 nanometers. Okay. So that is the largest possible wavelength given that m equals 1. Okay. That is the largest possible wavelength. Just to show you, let me plug in 3. If you plug, I'm not going to show all the work for it. I'll just write here that if you plug in n equals 3, what you get is that the wavelength, well, you basically have 1 minus 1 over 3 squared, which is 1 minus 1 over 9, right? Which gives you 8/9 here. So the wavelength in that case will be 1.026 times 10 to the negative 7th meters, which is approximately, if we put that in nanometers, 102.6 nanometers. So notice here that if n equals 3, we have a wavelength that's a little bit smaller, but it's the next biggest, right? So you can imagine that as you plug in numbers for n that are bigger and bigger and bigger, the wavelength that you end up getting is going to be smaller and smaller and smaller. Okay, so then they ask you, what would be the shortest possible wavelength? So all of this work was for A, right? Part A. Now let's do part B. What is the shortest possible wavelength? Well, we're still going to use this equation here solved for wavelength, right? Wavelength equals this, right? That's the equation we're going to be using. So 1 over r times 1 over 1 squared, or actually I'll just plug this all in here because we know what r is already, 1.097 times 10 to the 7th, 1 over meters. And we know that m equals 1, so we'll have 1 over 1 squared minus 1 over n. Now, the question is now what to put in for n. Well, we want the shortest possible wavelength. Well, in the case of the previous example where we had the longest possible wavelength, we had to make n as small as possible, just keeping in mind that n had to be bigger than m. So we just picked the smallest integer that's bigger than 1, which was 2. But now, we want the shortest possible wavelength, so we want n to be as big as possible. So I'll write that here. So n as big as possible for part B. Okay, so, but I can go on for integers forever, right? So what can I put in here? Well, if I can go on forever, what does that really mean? That means infinity, right? So if I put in infinity here, what that basically makes happen is that 1 divided by a really, really, really large number is effectively 0, right? So I have 1 over 1 squared minus 0, which is just 1, right? So then I'll have 1 over 1.097 times 10 to the 7th, 1 over meters, times 1 over 1 squared minus 0, which is 1 minus 0, which is just 1. And if I plug that in, I will get 9.116 times 10 to the negative 8th meters, which is, in nanometers, 91.16 nanometers. Okay? So that would be the shortest possible wavelength when n is as big as possible, which is infinity. Okay? So notice that, of course, this value is smaller than this value. This is the biggest, this is the longest possible wavelength, and this is the shortest possible wavelength, assuming that m equals 1. Okay. Hope that video was helpful. Thank you for watching. If you found that video helpful, don't forget to like, comment, subscribe, and share with friends. Thank you, and happy studying.